Hey guys, this is Professor Schmidt, and let's look at problem 1 from this section on sex determination. It reads, a human individual with Klinefelter syndrome has an XXY genotype. Determine if each of the following events could give rise to a Klinefelter's male. And we have non-disjunction occurring either at meiosis 1 in the mother, meiosis 2 in the mother, meiosis 1 in the father, or meiosis 2 in the father, A, B, C, D. So I think what's important to realize before we start this one is we have to realize that in the case of Klinefelter syndrome, XSY is basically the definition, so that makes sense. But the problem could lie, in theory, in gamete production in the mother or in the father. Now, if the problem, let's just say, if the problem's in the mother, then the only place the Y can come from is the male, so that's a normal male gamete, right? What we're really asking is, can the mother make a gamete that's got two X's in it? In other words, the two X's that she had failed to separate, which is what non-disjunction means. In the case of the father having a problem, remember that the father is XY, so if the mother makes a normal gamete, it'll just have an X in it, right? So we're really asking, in this case, can the father make a gamete that is XY, which is the same idea. Like he is XY, so they failed to separate. So really, in question A and B, we're asking ourselves, whether it's meiosis 1 or meiosis 2, can this lead to the production of an XX gamete in the mother? And in the case of C and D, we're asking, can it lead to an XY gamete for the father? So let's check it out and see what happens. We're only going to consider the sex chromosome pair. That's all we need to consider for here. So let's follow meiosis 1 and meiosis 2 in the mother, right? Here's a cell. And in meiosis 1, we would have the doubled X chromosome lined up with the much, much smaller doubled Y chromosome there, right? Now that's silly. Why did I do that? Were you just yelling at me? The mother doesn't have a Y chromosome. I don't know why I was thinking of that. She has both of her X's. I'm so sorry about that. You know, I can erase this and do it over, but I want you to realize that even me makes silly mistakes, and I'm not proud of it, but it happens, and we have to be vigilant and we have to be careful about doing these things. So the whole point, remember, of meiosis 1 is to separate the homologous pairs. What if they fail to separate? What if, in other words, what if non-disjunction occurs here in meiosis 1? Well, what's going to happen is we're going to make two cells, one of which is going to end up with both of these gametes in it, both of these X chromosomes in it, and one which is going to end up with nothing in it, right? And then, if that same cell undergoes meiosis 2, it's going to be strange, but what's going to happen is, well, let's think about what's going to happen. Normally, what should be in a cell at meiosis 2? Just this one. And the sister chromatids are going to separate, right? But now we have floating around this other X. So in other words, we're assuming meiosis 2 is going to go right. But even if it goes right, what's going to happen? We're going to make two cells, each of which have two X chromosomes in them. And if this fertilizes a male's normal Y containing gamete, you're going to get XXY. So the answer is, if non-disjunction occurs, which is, you're seeing it happen right here, this is meiosis 1, right? Since non-disjunction occurred, you end up with imbalanced cells here. One got both of the X chromosomes, one got nothing, and that did lead to the production, at least in many of the gametes, of double X's. So they asked us, could this event give rise to a Klinefelter's male? The answer for A is yes. So let's erase this and ask ourselves basically the same question, though, and say, well, what if meiosis 1 went okay, but meiosis 2 is where the problem lies? All right, so we're starting off with that same cell, and now we're saying, okay, meiosis 1 is going to go well. So if meiosis 1 goes well, remember that the point of it is to separate the one doubled homologue from the other. So that's all well and good. But now we just really have to look at one of these cells. If they fail, what's the whole point of meiosis 2? It's to separate these so that in the gametes you'll have only one, right? So what happens if it fails to separate now? We're going to have one gamete. You know, I keep saying it is a gamete at this point. I hope that I've been consistent in my terminology. We're going to have one where it failed to separate. So one gets the whole entire thing, and one gets nothing. And this is going to be possible that it can meet up with a normal male Y, and you've got, they're still sticking together on there, but they don't necessarily have to stay there. But there's two X chromosomes in that gamete. It's not good, it's imbalanced, and you can get an XXY male from there. So the point is, it's not exactly the same, but whether non-disjunction occurs at meiosis 1 or meiosis 2 in the mother, both of those things can cause the production of gametes that have two X's, which is, remember, what the whole question we were asking over here was, and they can create a Klinefelter's male. Now let's check out what the situation is with the father. Remember, we said the question is, can we get an XY gamete? So here's the father's cell, and during meiosis 1 now is when we want to draw one X, and I'm not going to be able to draw the Y very accurately, but let's just make it a little bit smaller. But the point is, if non-disjunction occurs at meiosis 1, just for the same reason as before, remember, these are supposed to separate in meiosis 1. One cell's going to end up having all this material in there if they don't separate, and the other one's going to get nothing, right? And then when meiosis 2 comes around, what's going to happen with this cell? Well, normally the sister chromatids get pulled apart, and assuming meiosis 2 happens properly, they will get pulled apart, but we'll have two cells that have both an X and a Y in them, right? And if they meet up with the normal X from a normal woman, you're going to have X, Y, X, which is the same as XXY. So the answer is yes for C. You may be starting to think the answer is yes for everything. You might be right. We got to find out. All right. Non-disjunction at meiosis 2 in the dad. So here again, I shouldn't have erased that part. And I should also learn to draw. But I'm hoping it's good enough for you guys. All right. So now we're assuming meiosis 1 is going to be fine, right? Which means that we're going to get one cell that ends up with the X chromosome in it, and one that ends up with the much smaller Y. Now, if non-disjunction occurs in meiosis 2, remember, the only relevant question here is, can this guy make something with an X and a Y in it? Well, here's the only Y. And if non-disjunction occurs here, we're going to have a cell with two Y's in it and another cell with nothing. If that met up with a normal X from a woman, you'd get XYY, not XXY. So the point is, if meiosis 1 goes okay, the X and the Y have already separated from each other. And, you know, even if this created, if non-disjunction occurred in the one with the X, you'd get two X's, you'd get XXX if you met up with a normal gamete. So it's not to say that different types of problems can't happen, but Klinefelters cannot happen. So finally, we get a no. A Klinefelter's, a gamete that will lead to Klinefelter syndrome cannot be produced at meiosis 2 in the father. All right, well, that was quite interesting, and I'm sure we'll see one another. Well, in this context, hear one another? No, I can't hear you. I'll talk to you soon, guys. Take care.
Question 2 asks, how many Barr bodies would humans with the following hypothetical genotypes have in each cell? So remember that Barr bodies is a form of dosage compensation because the correct human dose for X chromosome is only 1. So for every other X chromosomes after that first one, they are downregulated into a bar body that isn't expressed. So for A, this is a normal female. She will have 1 bar body. And that's because she only needs 1 of her X chromosomes. For B, that's a normal male, and because the human dosage for X chromosome is 1, he will have no bar body, so that's 0. For C, that's actually an individual with Klinefelter syndrome, and because again you only need 1 X, this person would have 1 bar body. For D, this isn't really possible, but again this is hypothetical. So again you only need 1 X chromosome, so this individual would have 3 bar bodies. And for E, this is Turner syndrome, and you only have 1 X and you only need 1 X, so again this would be 0.
Question 3 says the following. Haploploidy is the system of sex determination in honeybees. In this system, males develop from unfertilized eggs and are haploid. Mitotic division in these males give rise to sperm, which can fertilize eggs in the females, producing the diploid female. Long wings are a recessive characteristic, and short wings are wild type. Now, a couple of things before we go into A and B. Haploploidy, it's okay to say, but very often you will hear this same system referred to as haplodiploidy. It depends on the professor and it depends on the textbook. So if you see haplodiploidy or haploploidy, it means the same thing as far as any circumstance I've ever seen. Also, I'm hoping that you'll see this, but they're saying that long wings are recessive and short wings are wild type. They didn't specifically say that it's dominant, but in this type of a question, you can assume that because if it's not recessive, it's dominant. Now, specifically, they're asking us if a long-winged female and a short-winged male reproduce, what offspring would result? Give genotype and phenotype for offspring produced from fertilized and non-fertilized eggs. In other words, who are the males going to look like and what are the females going to look like? Haplodiploidy can drive you a little nutty sometime, but it's not so bad in a cross like this. It's very important that we write down the genotypes of each of these individuals. So first, the long-winged female. The females are diploid. And since long wings are recessive, right, the female has to be little l, little l. That looks like the number 11, but it's little l, little l. Now, we have a short-winged male. Short wings is the dominant trait. You know, I just realized the proper convention is, you can do whatever you want, but the proper convention is to usually use the letter for the dominant trait. So let's say that, apologize for that, let's say that big S equals short, little s equals long. Okay? So instead of being little l, she'll be little s. That's the convention that Mendel did with the pea plants anyway. She is being crossed with a male, and he is short-winged. So he's haploid, though. So he's only got one or the other. And if he's short, he's got big S. That's all it is. So look what happens. The male flies make, these are bees, in fact. There are various insects that use this type of system. Flies, in fact, are not really one of them. But the bees, in this case, the male bees, make sperm, but they make it by mitosis. So if we go to do a Punnett square about this, we're going to have a couple of situations. The female makes a gamete via meiosis in the traditional way, so she can have little s or little s, basically, right? The males make sperm that can only be big S. Conventionally, we would put another one over there, but in this case, nothing was separating, so there's really no point. But here's something that's really important to understand. They said what would happen from the fertilized eggs and from the non-fertilized eggs. You don't even have to do a Punnett square to think about the non-fertilized eggs, because this is it, right? So a non-fertilized egg will grow into a male. Males come from unfertilized eggs. So all the males will simply equal little s, and that means long wings, right? So all the males from this cross, what they mean when they say up here, produced from non-fertilized eggs, those are the males, and we see there's only one way for them to be. So all the males are going to have long wings from this first cross in A. The females come from the fertilized eggs, which means big S, little s, big S, little s, right? They're all going to be the same, and since big S is dominant, they will be short-winged. So we have females that are short-winged, but they are also heterozygotes, and we have males that are long-winged, and the term hemizygous, I don't even know if it should be used here, but they only have one. That's the bottom line. So that really isn't so bad. It just, again, as always, really arranging it, asking yourself what it is that they really want to know, and setting it up correctly. Now, part B is a little bit more difficult. If one of the female offspring from the previous cross mated with a short-winged male, what would happen? So let's extend our page a little bit. And because I think we can use some of the information we already have. So if one of the female offspring from the previous cross, note sometimes they do this, it's a little bit annoying. My point being, if you got part A wrong, then you're going to probably get part B wrong as well, because they're not specifying it. They're saying from the last cross. So if you did it wrong in the last cross, you're going to do it wrong in this cross. But we know the female offspring are big S, little s, right? So just like we wrote across here for part A, let's write across over here for part B. The females are big S, little s, and they're crossing with a male. They're telling us what it is. It's a short-winged male. Since short is dominant and males are haploid, that's the cross, right? Now, remember, we can do our Punnett square, and we're going to actually need to here, but the males come from unfertilized eggs. So let's do a Punnett square, because here's the thing. Females can make gametes, eggs, that are big S or little s, right? So right off the bat, realize, look what we did before with this line here. We just said those are the males. So males, without even doing anything else, we're going to say half of them are going to be big S when those unfertilized eggs develop, and half of them are going to be little s. And what does that mean? That means half short, half long, right? Easy peasy. The females, on the other hand, so the male is big S. That means he's going to be making sperm that are all big S. Females come from fertilization, so they could either be big S or big S little s. So females, phenotypically, aren't they all going to be short because they both have a big S? Short is dominant. All short. They did ask us, at least in the first one, they said give genotype and phenotype. So just for the record, half of the females would be homozygotes, big S, and half would be big S, little s. That's fun, haplodiploidy. I will see you guys soon. Let's look at question 4. Non-disjunction in gametogenesis can lead to offspring with abnormal genotypes. Determine if non-disjunction in the female can lead to the following, assuming fertilization by a normal sperm, and explain. Okay, I'm not sure if you're doing all of the problems, but we did one earlier in this section that's somewhat similar to this. Basically, here though, we're asking, assuming fertilization by a normal sperm. So in other words, a normal sperm, since men are XY, right, can either, here's a sperm, have an X chromosome in it or a Y chromosome in it, right? So those are the two options for a normal sperm. So we've got to ask ourselves, so with A, right, if you're going to get XXX and a normal sperm's going to be involved, it would certainly have to be that one, right? So the real question is, can non-disjunction in the female make a gamete that is XX? And we've already seen, if you have done the other problem, that the answer is yes, but let's quickly do it again. So here is a female with her two X chromosomes. Meiosis I is supposed to separate the homologs. But if that fails, you're going to end up with one cell that has two X chromosomes in it and one that has 0. And meiosis II is supposed to pull apart the sister chromatids, and if it does that, it will lead to two gametes that have two X chromosomes in there, and that's exactly what we're looking for, and two that have nothing in there. When I say nothing, I don't literally mean nothing. I mean nothing with respect to the X chromosome. Okay, so if this gamete here fertilized that norma male 1, you would get XXX. Now, that's enough to really answer the question because you say yes, it can. We just showed you how. But if non-disjunction occurs in meiosis II, just for the record, it can still happen because say meiosis I goes fine, then you end up like this, right? But if non-disjunction occurs in meiosis II, again, you'll get one gamete that has both the X's in it, one that has none. These two would be normal. So whether non-disjunction occurs in meiosis I or meiosis II, in fact, I'm glad we did this because it's going to help us very much just in a second. Because we're seeing here are the 4 types of gametes that can be made if non-disjunction occurs during meiosis I. They're all imbalanced. Here, if it occurs in meiosis II, we get 2 that are imbalanced and 2 that are normal. Now, with B, can you get an XXY, which is a Klinefelter's individual, from, again, non-disjunction and fertilization by a normal sperm? Well, clearly the Y is going to have to come from the sperm, right? So the question is exactly the same. Can the female make a gamete that's XX? We just saw 2 ways that she can do that. So the answer is yes again. So determine if, yes. Now what about XO? This is interesting because we're saying a normal sperm has to be the fertilizer, and that means a normal sperm has to have either the X or the Y. So in this case, the normal sperm would have to be supplying the X. And what does XO really mean anyways? It means O refers to nothing. There's supposed to be a pair there, but there's just an X. So what we're really asking is, can females make gametes with no X chromosome in there, with nothing, as we said before? And we saw before, here's 2 right here if it happens during meiosis I, and here's 1 right there if it happens during meiosis II. So once again, the answer is yes. You'd have a normal sperm that was X being fertilized by an egg that has basically nothing in there, and that's what XO looks like. OX, but XO is the same thing. So yes, yes, yes. In fact, all 3 of these conditions can occur due to non-disjunction in the female. They didn't ask us about meiosis I and meiosis II, but we said it anyway. And this is very importantly assuming fertilization by a normal sperm. Okay, question 5. A pregnant couple, well, I assume the woman is the one who's pregnant, decides to have an amniocentesis and karyotyping performed to look for genetic abnormalities in their unborn child, the fetus. The test results show that the child has 47 chromosomes, normal autosomal pairs, autosomal pairs, meaning everything but this X chromosome is good, and X and two Ys. So we would say that this child basically is X, Y, Y. And this is a condition that does occur. So this might not be as bad as you might think, though. Will the child be male or female? I was going to say you all know, but I think you all know that maleness, as it were, obviously this gets more complicated, but generally speaking, if there's a Y chromosome present, a child's going to be male. If it's absent, the child's not going to be male. So having two Ys will still have you be male. Did the abnormality result from a non-disjunction event in the mother or the father? Well, we don't have to really draw out bunches of diagrams and everything, because look, if there are two Ys, right, there had to have been a problem in the father. It just has to be, right? Because, look, the mother's XX, no matter what kind of non-disjunction event occurs, she could have gametes that are X, which is normal, XX, or pretty much nothing, right? But none of those could possibly explain how two Ys got involved in there. The non-disjunction had to occur on the father, and Part C will allow us to take a little look at how that probably happened, or how that definitely happened. Because, and I'm sorry to say this all the time, but we've already solved this in another one of the problems, in a sense. Here's the father. He's got an X and a Y, which is hard to draw, so we're just going to make it smaller. If non-disjunction occurs in meiosis 1, what will occur is that all this material, it's a failure to separate of the homologs, right? So all this material will end up in this one cell, and this one will have nothing. And then these will still have nothing. You basically get an XY gamete and an XY gamete. If any of these fertilize a normal female gamete, you're either going to get XXY, which is Klinefelter syndrome, or XO, which is Turner syndrome. There's no way to get XYY this way. So non-disjunction did not occur in meiosis 1. It must have occurred in meiosis 2, but let's just see why that's got to be. So we're assuming that meiosis 1 occurred normally. That will give us two cells where the homologs separated. So one has a duplicated X in it, one has a duplicated Y. If non-disjunction occurred here, the male actually could make a gamete that has two X's in it, but again, that's not going to explain where two Y's came from, right? Two X's and nothing. But if non-disjunction occurs here, a failure to separate will give us the two Y's in that one and nothing in that one. So the only way to get a gamete with two Y's in it is if non-disjunction occurs during meiosis 2. And that's really all you have to do for this problem. It makes it sound easy, right? But it's not that bad.